Hello, I'm Carolyn Chapel, and I am going to be doing a video here about probability trees or the use of probability trees in conjunction with conditional probability. And this is my second example. I did a video earlier or at another time, so feel free to look at that one as well. This one is going to be using something more on a medical field. So I want us to consider this information. We're going to consider a very rare disease. Suppose that the probability of getting this disease is 1 out of 1,000, or if you're doing it in decimal form, 0.001. And we're going to suppose even further that the test for this, whether it be a blood test or some other type of test, is 99% accurate. Okay, and the first thing I'm going to do for this is to draw this tree. So let's say here you are. So again, when I draw my trees, I like to think of me in this situation. So here I am. And of course, I am going into the doctor for whatever reason, and they're going to perform this test. Well, even when I'm walking in the door, there's two possibilities. Either I have this disease or I don't have this disease. So I'm going to use healthy, an H, for being not having this disease. And I'm going to use an S for sick, meaning I have this disease. Now, since this is a very rare disease, the chance that I am sick is just 0.001. So I'm going to put that probability in here right away. And the probability that I'm healthy, well, that's everybody else. So remembering that probabilities have to add up to 1. This means that probability that I'm healthy is 0.999. Okay, now I go into the doctor and they give me this test. Now the tests come back either a positive or a negative. In either case, I'm going to put my positive in here or my negative. Now the probabilities depend on, again, it's 99% accurate. So if I am healthy, an accurate test would be the fact that it came back negative, saying I don't have this disease. So that 0.99 will be on that negative piece, where then the positive would be that 0.01. Down on this branch, if I am sick, the accurate test would be that positive test. So that's where the 0.99 comes in. And this would then be that 0.01. Okay. Sometimes you may have heard the terms false positive or false negative. A false positive would be in this situation up here, where you have a positive test come back. So there's the positive part, but it's not true because in reality, our person is healthy. So it is a false positive. That idea of false negative comes down here because the test comes back saying you're negative, meaning it doesn't show you have the disease, but in reality, you do. So here's our false negatives. Okay, so what we're going to do is I'm going to kind of complete this piece. And if you can remember from previous of my videos or from your other statistical knowledge, that if you have a tree and you want to find out they're healthy and they have a positive test, we can use that general multiplication rule and multiply those together. So here we're going to get 0.00999. Here we could multiply these. And this would be our healthy positive, or healthy and a negative. So H and negative. So this is 0.98901. Here we have multiplying these together. And that would give me 0.00099. And multiplying those two together, a very small amount, 0.00001. Okay, so there's my complete tree. Sometimes you don't necessarily need to go all the way to here because you might not need all of these branches completed, but I did them just for sake of completeness. And now I'm going to basically do some questions here and see how we can use this tree to answer some questions. So we're going to choose a person at random. So someone out in the world, and we're going to give them this test or whatever, and we want to know, given this person, based on this information, what is the probability that they are healthy and would get a negative test? Okay. So this is my healthy and negative test. That is actually this branch right here. So that would be my 0.98901 that I had calculated before. Okay. What if I just wanted to know what's the probability that a person at random would receive a positive test? Okay. So getting a positive test, well, we don't know whether or not they're healthy or sick. We just want to talk about all our positive tested people. And that's this branch up here, or we could have been down here at this branch. So now remembering that these two branches are mutually exclusive, they have nothing in common with one another, which means we can simply add those two numbers together. 0.00999, and we're going to add that 0.00099. And if I add those two together, we get 0.01098. Okay. And the next question I'm going to ask, we're going to have a kind of a strange result when we get that. Because a lot of times we don't know if we are healthy or if we're sick. And a lot of times we would rather be, if you get that positive test coming back, you'd be like, oh my gosh, I'm going to die because you had this rare disease and now all hope is lost. So what I'm going to do is we're going to actually calculate what the probability is that we are sick, given that we got a positive test. So we went to the doctor, not knowing if we're sick or healthy, because we don't know. We had this test performed. It comes back and it's positive. Okay, so remembering some of the things that how conditional probability works. Calculate that probability. We are going to calculate, first of all, that probability of sick and a positive test over the probability of that given piece. Okay, and this comes directly from the definition of a conditional probability. We have talked about it in my videos anyway, about restricting the sample space down. So just knowing that we are on those positive test pieces. So we're out of these two guys. To calculate this, we will look at that sick and positive. So our sick and positive pieces, that's this guy right here. So that's my 0.00099 over the probability that we have that positive test, which is the answer that we just done previously. Kind of why I did that, because I knew where I was going in this video. And if I actually do this division, it turns out we have 0.09016. So the test comes back positive. And now you only have a 9% chance that you are truly sick. And you're thinking to yourself, how can that be possible? So I kind of want to show you what's going on. Because the numbers seem strange, and if I were doing this problem as a homework question, I would be like, well, that can't be right. But it is correct. And the reason is because this is such a rare disease. Okay, so I'm going to kind of draw a picture to kind of help explain what's going on. So let's imagine that we have, oh, I don't know, a group of people. Okay, so there's a group of people, and let's just make the numbers easy. Let's say we have 1,000 people. Okay, so we've got all these people in here, and there's 1,000 of them. I'm not going to draw 1,000 little X's to represent our people. But I do know that this disease only affects 1 in 1,000 people. So here is my sick person. Okay, and that means I have 999 healthy people. 999 healthy people. And 1 sick, right? Because this is a 1 out of 1,000 chance that you're going to be sick. So we have 999 healthy people. Now, our test is 99% accurate, but it's also 1% inaccurate. So of those 999, we take that and multiply it by that 0.01. That's at 1% of inaccurate pieces. We will see that they will get, I'm going to take that 999 and multiply that by 0.01. And we're going to get roughly 9.99. I could have probably done that in my head. Would get a positive test. Okay, I'm just going to round up to 10 just to make this a little bit easier. So that means of my healthy people, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's our 10 healthy people who tested positive. Yeah, so now we have basically, I'm going to group this guy in and saying that this sick person does test positive because it's more likely he would. Being at 99% accurate, it's more likely that this guy would test positive. But now we have basically 11 people who tested positive. So out of these 11, only 1 is truly sick. So 1 out of the 11. And if you do calculate, this is like 0.090909, if I remember correctly from doing it earlier. Yeah. Okay. This is roughly the idea. Our answer was not quite that. We had 0.09016. The reason for that difference is because we did round up here to 10. And I did assume that this person would be tested positive. But for this argument, you can kind of see that, oh, yeah, I'm not going to have that likely of a chance, simply because since the test is inaccurate, we're going to have a lot of people that are going to test positive that are really truly healthy. So this is sometimes why if a disease is rare enough and you have a positive test, they want you to get tested again, or they will do another test just to make sure. It doesn't happen if the disease is rare that if you get a negative test, that it's more likely you're sick than not sick. But it does happen this way a lot of times with that false positive. So we kind of get a little bit overwhelming stress-wise when you get that positive test. But note if the test isn't accurate enough, 99% seems pretty good, but on a very rare test, we do strive to get even more accuracy on our testing. So hopefully this gives you a little bit more of an insight into how these probability trees and how the conditional probabilities, so this was a conditional probability, can be used in the real world. So they've done the mathematics or the numbers and the statistics in a lot of our medical field, and these things do make a difference to us. So I hope you enjoyed the video, and I hope you got a little bit more insight into the world of statistics, and I'll see you in another one.